So today we're going to talk about changes in motion, and anytime we talk about changing motion, we have to talk about force, which is the reason for your bell ringer being about forces today, okay? Our goals for today is that you'll be able to define what a force is and identify forces happening in a situation. And then also, we're going to learn a physics skill, which is to draw a free body diagram, okay? So if you cannot do those things by the time class is over, you should check in with me, because that's what our goal is. Beginning with forces. Forces are actions exerted on objects that change an object's state of rest or motion. So the elementary definition that we've had for forever of a push or a pull fits into this definition, right? A push or a pull will change an object's state of rest or motion. If the object is moving and you push on it, you can change its direction, or sometimes you can change its velocity. You can stop it or make it go faster. Okay? If you pull on an object, similar things can happen. So anything that you are doing to an object that causes it to change its motion can be classified as a force. Forces change an object's velocity with respect to time, which means they are affecting the acceleration of the object. So they can cause it to speed up. For example, if you throw a ball, you cause that ball's velocity to increase, so you're causing positive acceleration. You can slow something down. So if you throw a ball and your friend catches the ball, they are causing its velocity to change, slowing it down. So that is acceleration. And they can cause the object to change direction. If you pitch the ball to your friend and they hit it with a bat, they are going to change the direction in which that ball is moving. So even if they don't change the velocity, the magnitude of the velocity, they're still changing the direction, so they're affecting the velocity, so it is said to be accelerating. The SI unit that we're going to use for force is the Newton, spelt with a lowercase n. Okay. It's named after Sir Isaac Newton, who was a great contributor to our understanding of forces and motion. Okay. So we honor him and his contributions to this science by naming a unit after him. Okay. A Newton is the amount of force that, when acting on a 1 kilogram mass, produces an acceleration of 1 meter per second squared. So however much force that actually is, that's what we define as 1 Newton. Therefore, 1 Newton is equal to 1 kilogram times 1 meter per second squared. Weight is a measure of gravity and how much gravity is exerting a force on an object. So, you will often see weight be referred to in newtons in this book, because anything that is measuring the weight of an object, not the mass, but the weight of an object, is actually a unit of force and not a unit of mass. Okay, so a gram, that's a unit of mass. That's not measuring gravity's effect on something. That's measuring how much matter is in an object. But a pound is measuring the pull of gravity on that object, so it is a unit of force. One Newton is actually equal to 0.225 pounds. So if you ever wanted to know the conversion between newtons and pounds, there it is for you. Forces come in two general types, at least when we're talking about macroscopic objects. They come in two types, okay? The first type is the one you're probably the most familiar with, which is contact forces, okay? The name says it all. These are forces where the two objects come into contact with each other. There's actual physical contact, the objects are touching. That has to happen in order for it to be qualified as a contact force. They're often easy to identify because you can actually see them visibly. Examples: pushing on a door or pulling on a leash. Okay? If you're pushing on the door, your hand has to actually physically contact the door. If you're pulling on a leash, your hand has to be in contact with the leash. So that makes these contact forces. The second type of force is field forces. These do not involve physical contact between objects. Okay, the two objects do not actually have to touch in a field force, okay, which is why they're often not visible, because you can't see two objects that are not touching. You can't see that force, okay? Examples of this type of force: gravity, right? We experience that every day. The earth pulls us to it, but we can't see the actual physical representation of that force on us. And then the attraction and repulsion between objects that have electric charges. Those are another example of a field force. Now, air resistance is a tricky one because you don't see it, correct? Yeah. But it is a physical force, and the objects are actually touching, right? It just so happens that one of the objects that is touching the other object is not visible to the naked eye. Okay? So it's still a contact force. That's why I say, something not being visible doesn't necessarily mean it's a non-contact force or a field force. It just means that you have to actually know if the objects are actually touching or not in order to tell the difference. And then it bears pointing out that this holds true at the macroscopic level, so at the level at which we see the world, but it kind of breaks down a little bit if you go down to the microscopic level, where all forces are actually one of four fundamental field forces. So this comes back to what we were talking to about, science is fake, nothing is real, you've never touched an object a day in your life. You just think you have, because at the macroscopic level, field forces between atoms of your body and atoms of the objects that you think you're touching are interacting and giving you the impression that you're touching something. But you're not. Life is an illusion. Force diagrams. Okay? Force is a vector. The acceleration of an object depends on the force's magnitude. So how much you speed it up or slow it down depends on the strength of the force, the magnitude of the force. Okay? And the direction that the object is going to accelerate in is going to depend on the direction from which the force is applied and in which the force is applied. So, for those reasons, we say force is a vector, because both magnitude and direction are involved. It is considered a vector. We will be drawing some diagrams in this chapter to represent forces, and in these diagrams, there are a few things that you should remember. Okay? First of all, we're going to represent forces using arrows. So every force will have an arrow that goes with it. The size and shape of the object is neglected, so force arrows are always going to be drawn from the center of the object. So even if you're dealing with a long object like a train, you're going to draw your force arrows, both ones that are acting on it and ones that are coming off of it, from the center of the object. Okay? Even if they hit the engine of the train, you draw it from the center. Arrows point in the direction that the force acts in, and the length of the arrow is going to be proportional to the magnitude of the force. So longer arrow, greater force. Shorter arrow, weaker force. Let's give this a try. What I want you to do is grab one of my toy cars and a book, and then I want you to roll the car into the book and model a crash. Okay? While you're doing that, Observe as many different changes in motion as you can for the car, and make a list of all the changes you see and try to identify what forces caused those changes. Okay, be prepared to share. So, what forces did we see acting on the car?
When we push on it.
Okay, so there's a push force from you, so causing the car to move. Okay, what other forces do we see? Friction, okay, between the wheels of the car and the table. What other forces?
When it crashes.
When it crashes, it comes back a little bit. So that force is caused by what? Probably the wall, right? The thing you ran your car into. Okay, so if we were gonna force diagram this, we'd start by drawing our little vehicle. Okay, just a simplified version of him. Okay, and then probably draw our wall or book or whatever you want to call it. Okay, so remembering that the forces are going to start from the center of the vehicle, right? In which direction should we draw arrows off of this car? What do you think? And why would we draw an arrow pointing down? I'm not saying we shouldn't. I'm asking why you think we should draw an arrow pointing down. What force does everything on Earth experience? Gravity, yes. So it's not incorrect. It's not incorrect to draw a force down. Okay. Now, this car, is it sinking through the surface of the Earth? No. So what else is probably pushing on this car? Yeah, the table, right? So if it's staying there, one thing we can know is that the force of gravity and the force from the table should be equal and opposite. Okay? And then we said that we applied a push force on this car. Okay? If it was a vehicle driving under its own power, we wouldn't necessarily draw a push force, but we did push on it. Okay? And we said there were forces from friction and from the wall that were acting in the opposite direction to this vehicle, right? So we could have forces going backwards for that. If we were going to draw the forces on the wall, we'd have the same up and down forces we had on the car. What other force would we have on this wall? Yeah, the impact from the car, right? Which would be in this direction. Good. Good, good, good. So I was just going to have you draw it. We drew it together. Okay. Now let's talk about free body diagrams. Okay. So in a free body diagram, what we're trying to do is isolate one object and talk about only the forces acting on that object. Okay. So just the forces on that object, not any of the forces it is applying to other objects. Again, just like before, we're going to have a basic image of that object. We're not going to make it super huge and complicated because it doesn't really matter because we're drawing all the forces from the center of it. But we want to be representative of it so we can tell what we're talking about in our diagram. Forces are going to, again, start from the center of the object and point in the direction they act in. We're going to, like I said, only show forces acting on the object, none of the other ones that the object may exert on other things. And we're going to have arrows that show both direction and magnitude of those forces. Later in this chapter, we're going to draw free body diagrams and analyze them just like we analyzed the vector diagrams from the previous chapter. So you will be coming up with component and resultant vectors for force as well as just like you did for like acceleration or velocity or things like that in the previous chapter. So we are going to try this out. We're going to skip past this. We're going to just try it out with our example problem. What I'd like is for you guys to try this example, okay? So it says, in the early morning, a park ranger in a canoe is observing wildlife on the nearby shore. Earth's gravitational force on the ranger is 760 newtons downward, and the gravitational force on the boat is 190 downward. The water keeps the canoe afloat by exerting a 950 Newton force upwards on it. Draw a free body diagram of the canoe. So I'm going to give you a moment to try this on your own, and then I will draw it up on the board for you. Okay, so in order to draw the free body diagram, we have to first isolate the object that we're drawing it for, which they have asked for the canoe. Okay, so we're just going to draw in a nice, lovely little basic canoe shape. Okay? Then we need to identify the forces acting on it, which they have been very nice for us in this particular one, and they have identified the forces for us so that we don't have to do a lot of the work here. Okay, so they said there is a 760 downward force on the ranger, okay, and we know if that force is on the ranger is exerting that same force on the boat, because that's what he's in. So that force plus the downward force on the boat is going to be our downward force on this diagram. So we would have a shorter arrow for the 190 Newton force, and then a longer one for that 760. So you could say force of ranger on canoe, and then this one up here is force of gravity on the canoe. Then we want our upward force to roughly match the downward force in length, because it's supposed to be balancing it, right? Which is how this boat is floating. And so then that would be the force of the water on the canoe. Okay? So you don't have to use the same abbreviations I do. You could write it out if you want, but some kind of indication of what each force is would be good. Okay? So these are the forces acting on the canoe in our free body diagram. And like I said, this one was kind of nice to you and clearly indicated which forces exactly were acting on this. Sometimes you're going to be given a scenario and you're going to have to pick out the forces yourself.